This is section 3.5, higher derivatives. We will investigate here higher derivatives of the function, since we know that when we take the derivative of the function, we gaining a new function. Yeah, the first derivative is a new function. And if this function is differentiable, like we can get the derivative f prime, and if the derivative is differentiable, we can differentiate again. Differentiating again, we're getting a second derivative. We can call second derivative of the original function f. And the notation, of course, it will be y double prime because it's the second derivative, or we can use the Leibniz notation, derivative with respect to x of the first derivative. This is the first derivative, dy dx. And then when we combine this notation, we do write this way. It looks like d squared and x squared, but it's not exactly squared. We will just read derivative of the derivative, the second derivative, and it was taken with respect to x and again with respect to x. That's the reason that we see dx twice. Okay, just the second derivative. And for instance, we remember from the previous sections, from the previous applications, velocity. Velocity is the rate of change of the distance over the time, and this represents the first derivative of the position function. When we will take the derivative of the first derivative of the velocity, we're getting acceleration. Yeah, we also learned this. Derivative of the velocity with respect to time is actually the second derivative of the original function, position function, with respect to time, and again with respect to time, because it's the rate of change of the distance with respect to time, velocity, and again with respect to time, acceleration. Okay, since we're getting second derivative, we may get also differentiable function, and we can try to differentiate again. We can repeat, repeatedly differentiate a function. Okay, that's differentiate, taking the derivative of the third derivative, we will get, taking the derivative of the second derivative, we will get the third derivative. And we may see the notation, y like triple prime, f triple prime, derivative of the second derivative. And this is the like compact Leibniz notation. We're not saying cube, we're just saying third derivative with respect to x. Now, if we will take the derivative of the acceleration, the rate of change of the distance with respect to time, and then again the rate of change with respect to time, acceleration, and again differentiating with respect to time, we will get something that is called jerk. I think it's a funny name. Jerk is like a, it's sudden, we will call kind of like a force, but we will say it's like a sudden change in acceleration. Okay? And if we would like to compute this, we will compute the third derivative of the original position function. Okay, and some of the functions are infinitely many times differentiable. We can take the derivative over and over and over again, and we will never reach zero. For some of the functions, we have to stop at some point, because at some point the derivative will be zero. But this means that we can have the nth derivative, and that's the notation. And we can differentiate infinitely many times. The functions that are differentiable infinitely many times are quite important in mathematics, because later we will need nth derivative of the function. That's why we have to make sure that this function is differentiable infinitely many times. And that's the notations, what we have to know. First derivative, second, third, fourth, and so on. Okay, let's practice. Calculate the third derivative at -1 for the given function. F of x equals to 3x to the power of 5 minus 2x squared plus 7x to the negative 2. Let's see how this function will behave. First derivative, 3x to the power of 5 is 15x to the power of 4. 4x, and this one will be negative 14 and x to the negative 3. So we may notice even after taking the first derivative, for the power function, we decrease the degree. And eventually this will disappear. The x, the variable, will disappear. We will get constant and derivative of the constant 0. But for this type of function, which is not exactly a power, it's written in the power form, but it's a rational function, because 7x to the negative 2 is just 7 over x squared, is the rational function. 7 times 1 over x squared, hyperbola. And taking the derivative, we didn't increase because we still decrease the number by 1, but it will not disappear because the numbers will go higher in the negative direction. That's kind of like an idea which functions will have infinitely many derivatives. Okay, let's keep working. Second derivative, 15 times 4, I think it's 60. And then 4, that's actually plus. And negative 3 times 14 and negative 4. I'm subtracting 1. Negative 3 minus 1 is negative 4. Okay, let's actually do the third derivative. This will be 60 times 3, 180 x squared minus 0, because a constant is 0. And this one will be, let me put negative 3 times 14 and times negative 4 and x to the power of negative 5. I still have to multiply these together. Okay, that's of course all of the power rule and the constant multiple. Okay, let's put nicely. The third derivative is 180 x squared. Negative and negative will give us positive. How can I manage without the calculator? 3 times 14 is 42, and times 4. I've already included the positive, negative, and negative. Okay, one more time. I know that I'm taking lots of room. 4 times 4 is 16, 160, 168. Okay, and that's the, oh no, I don't like boxing like this. Let's make it nicer. This is the final formula for the third derivative. But we can see the power functions, the x squared disappeared. The third derivative was 0. The third derivative was 0 for the quadratic function. Now let's finalize this question. We just have to substitute negative 1. 180 negative 1 squared, 168 negative 1 to the negative 5. Actually, just because we remember this is the constant, but x to the negative 5, I will rewrite as a 1 over x to the power of 5. It's just easier and nicer to have the final answer without the negative exponent. And we may see it's much, much easier to do some calculation, because if I will write negative 1 to the negative 5, too many negatives with different meaning. Yeah, like it's that negative 5 has nothing to do with a negative quantity. Yeah? This, of course, this is negative 1, and how we will know this. I mean, negative exponents are confusing for the calculation. And this one, if I rewrite this as a quantity negative 1 to the power of positive 5 in the denominator, then negative 1 to the power of 5, of course, is negative. The final answer is negative. And that means it's much, much easier when we have positive exponent. Okay, negative 1 squared, of course, is positive 1. This will be negative 1, negative 1 times 168 is negative 168, and the final answer is 12. I hope. I need my students to help me. I hope this is okay. Okay, 12. But of course, 12 is not a point of this question. We have different points on this example. Okay. Example number 2. Which of the following satisfies that this means that the kth, like derivative, the nth derivative, the kth derivative of the function f of x is equal to 0 for all k's greater than or equal to 6. That means if we will take the 6th derivative or greater, function will become 0. Yeah, we can probably figure out this exponent, this one, and this is x to the power of 1/2. That's not positive integers. This will always stay. When we subtract 1, computing the derivative, they will always stay. I mean, that's definitely not a case, because we will always have x to the power of negative number, negative half, and then negative 3/2, negative 5/2. This will be x to the negative 2, negative 3, negative 4. We just did this function. X to the power of 7/5. Taking the first derivative, we will subtract 1. It will be 2/5, and then negative 3/5, and so on. With, of course, coefficient, but I'm saying that's definitely not a good option. They will be never 0. Yeah? You probably know the answer, but let's see. Let's take this function because it's so easy to. Let's compute just the derivatives. 4x plus 25x to the power of 4. Second derivative is 4 plus 25 times 400 x cubed. And then the third derivative, that's 0. So we can see the quadratic function again. We need, if this is quadratic, the second degree, we need the third derivative to get 0. Yeah, because the second derivative will be constant. For the x to the power of 5, we will need the 6th derivative to be 0. Correct? We always need one number more. But let's check. 300 x to the power of 2, and then the fourth derivative, 600x, and then the fifth derivative is constant because was x to the power of 5. The fifth derivative is constant, and the sixth derivative is 0. That means, yes, the sixth derivative will be 0. Oh, of course, the other one, 7th, and so on, but we don't have to. But for this function, 1 minus x to the power of 6, we will not compute. I mean, it's probably not a challenge question, but for the sixth derivative, we will have constant. We probably know 6 times 5. I can even write this one because we'll have 6 times 5 times 4 times 2 times 1. Correct? Because we will have 6x to the power of 5, then 5x to the power of 4, and that will be the constant. And of course, the seventh derivative, one number will be 0. But we're not interested. We want this, the k number must be 6. That means the first function satisfies. This will still not satisfy because we need one extra. X to the power of 6 is too much. Of course, negative. Oh, actually, no. I have to be. Oh, no, negative. Okay, that's when we know when the derivative is 0 for the power function. Okay. Example number 3, let's just calculate just the first 3 derivatives of the function x e to the x. Product rule. derivative of x1 times e to the x plus x times derivative of e to the x, e to the x. I can, okay, let's just do this way. Second derivative, derivative of e to the x is just e to the x. And now we have the same thing like the original function. Derivative of x e to the x will be e to the x plus x e to the x. Then we have the second derivative 2 e to the x. That was the first derivative, 1 e to the x plus x ex plus x e to the x. And that's the second derivative, 2 e to the x. And let's compute the first derivative. Derivative of 2 e to the x is 2 e to the x, and then derivative of x is 1 times e to the x e to the x, because derivative of e to the x is e to the x. Okay, that means the third derivative is 3 e to the x plus x e to the x. And that's we can see the first derivative, 1 e to the x, the second derivative, 2, the third derivative, 3. If I will ask you to find the sixth derivative, we know what will happen. Or maybe the 40th. This will be 6 e to the x, x ex. 40 e to the x, because we know the pattern. Yeah? I can even write the nth derivative will be the n e to the x, x e to the x. It's nice when we realize the pattern. It's nice to have some formulas, shortcuts. Okay. Okay, example number 4. Find a value of n such that function y equals to x to the power of n e to the x satisfies the equation x times y prime equals to x, x minus 21 times y. Okay? So this is probably, for some of us, the first time that we see equation like this one. This equation contains x, the independent variable, and also contains y and y prime. Y is a function, and if we will not know what is the formula, we will say that this is like unknown function. We don't know what is the function. I mean, this equation again contains x, contains unknown function at the moment, and its rate of change, derivative. Okay, so in this type of equation, because we may have this type of equation, I was planning to erase without any like additional information about the y prime x. This type of equation we call differential equation. Equation that involves unknown function and its derivatives. And since the derivative is the first derivative, we will call the first degree differential equation. Yeah, the first order differential equation, because we have first derivative. Okay, but since we know function, it's a little bit, yeah, because we have the n, we don't know what is n. Let's figure out for what values of n this actually function is the solution of this equation. But we will not solve the equation itself. That's calculus 2. Okay, what I will do, we need also y prime, because y prime, we have to just substitute. That means y prime is the derivative, product rule. Derivative of x to the power of n is n x to the power of n minus 1 times e to the x plus x to the power of n times derivative of e to the x, e to the x. Okay, now I will copy this equation and substitute instead of y and y prime. X times y prime, x minus 21 times y. Okay, y prime is this. Okay, I can copy n x to the power of n minus 1 times e to the x plus x to the n e to the x, and then x minus 21 times y. Y is defined as a x to the n e to the x. Okay, I see common factor e to the x. I will factor out. And let's rewrite this. X to the power of n minus 1 is x to the power of n times x to the power of negative 1. And this will be x to the power of n. X to the power of n e to the x. One thing that we see e to the x and e to the x. We can divide both sides of the equation by e to the x because e to the x is never 0. That's when we okay. If we can divide both sides of the equation by a number that is different than 0, we fine. Okay, then we have x and also another common factor, x to the power of n. I will factor out. And then we will have n x to the negative 1 plus 1 because this is outside. However, x to the negative 1, I will rewrite without the negative exponent. X to the negative 1 is 1 over x. Okay. Okay. And then if we assume, because we don't exactly know what is x, but I can also divide both equations by x to the power of n. But I will just make the notes that x is not 0, just to make sure that we're not dividing by 0. Okay, x is not 0. Okay, then I will distribute. I will multiply x by this, and I will multiply x. We will have x times n times 1 over x times n times 1 over x, plus x, and x minus 21. This is actually gone, because it's x times 1 over x is just n. We do have n plus x equals to x minus 21. And if we subtract x from both sides, n is negative 21. In order for the left and the right hand side to be the same, quantity n, yeah, because we want the left and the right hand side the same. That's the purpose of every equation. N equals to negative 21. Okay, that's the solution. We did a little bit of algebra. Another one. Find all values of n such that this power function x to the power of n satisfies this. We would like to check which power, x to the power of what number, will satisfy this differential equation. X squared times y double prime minus 72y equals to 0. Okay, we can see the second order differential equation because we see y, unknown function, but we also see the second derivative, yeah? Second order differential equation. But we are not asked to solve this equation on its own. Again, that's calculus 2. Let's just substitute. Okay, we will need y, that's given. We will need the first derivative to get the second derivative because we don't have the first derivative in the equation. N, x to the n minus 1, and second derivative is n times n minus 1, x to the n minus 2. Okay, let's substitute x squared times the second derivative, n, I can write this way because I don't have expanded form, minus 72y, y is x to the power 72y, 72x to the power of n equals to 0. Okay, we have x squared. What we can do? Let's keep this for now, and this will be x to the power of n times x to the power of negative 2. We can divide by x to the power of n because we see here and we see here. Of course, 0 divided by x to the power of, maybe I can just not to be confused, I can take this term, this, and divide by x to the power of n. Of course, saying that this is not 0, because if we're dividing by 0. We're not even allowed to divide by 0. So we have to make this comments. This is gone. 0 divided by x to the power of n is still 0. Okay, what we have? We have x squared, we have n minus 1. X to the negative 2 is 1 over x squared. Minus 72 equals to 0. And we can see another cancellation, x squared and x squared. And then we have n squared. I can distribute minus n minus 72 equals to 0. We got nice quadratic equation. I hope we can factor out 72. Oh, we need some. Oh, we need the diff. Okay, we need factors of 72. Let's start from the beginning. I think I know, but I wish to have your help. 36 times 2. That's 72. But this is definitely the difference, or the sum is not 1, because I mean negative 1. Okay, then I can say possibly, what I can say? I can say 18 times 4, because then I will have 36 is 18 times 2. But the 18 and 4 is also not, the difference between them is not 1 or negative 1. Okay, now I can say 9 times 8, correct? Which actually I should say this right away. I don't know why I didn't. Okay, 9 times 8, oh my gosh, is 72. And the difference between them is definitely 1. Let's figure out the sign, negative, positive. I don't know, for some reason I thought about some huge numbers. Okay, n is 9 or n is negative 8. That's the answer. Of course, n9 will give us nice power function, x to the power of 9. Negative 8 is the rational function, it's 1 over x to the 8. But both of the numbers, both of the n values are satisfying this differential. I mean the function, the power, x to the power of 9, x to the power of negative 8 will satisfy this differential equation. Okay, and I have one more question. Let's figure out, okay, this is different, but it's still playing with higher derivatives, the first and the second. One graph is a function, one graph is the derivative, one graph is the second derivative. We have to determine which one is which. Okay, what we can do? We know that if function is, what we can start. We know a couple of things from the graph and the derivatives. Drawing a horizontal tangent, yes, drawing a horizontal tangent, like for instance, this horizontal, and this horizontal. I'm drawing for the red curve. If we have horizontal tangent, slope is 0. Slope is the derivative. Yes, slope is the derivative. Then value of the derivative, yes, value of the derivative supposed to be 0. And let's check. We do have 0 here. 0 and then 0. Wow, maybe I pick the function first. And 0. Okay? But let's check another thing. If this function is decreasing, its derivative is positive. And we can see the green graph is above the x-axis, positive. Oh, no. I think the session is too long. No. Decreasing. Wrong. I really wanted to see this. No. I mean this. One more time. Let's start. If the function is decreasing, Okay, that's wrong. If the function is decreasing, I can even write this, function is going down, then its derivative is less than 0, of course, less than 0. And actually, we may notice that the green function is positive. That means the green function, even if with that red dots, the zeros match, the value of the derivative being 0 at these points match, I don't think the graph match, because I will expect the green graph to be negative, yes, on that interval, and actually it's positive. I mean, that's not good. Let's look at different. That means we can start over. Let's look at this purple or blue, the purple color. Again, I can draw horizontal tangent, slope 0, slope 0, slope 0. Then the value of the derivative is supposed to be 0. Green function, 0 has 0. When this is slope, this is value 0. And oh, no, I'm not looking at the red. I can even remove that red. Red didn't work. Now I'm looking at the purple. This slope is 0 and the value of the green function. Oh, that means green function, green looks like the derivative, but let's double check. If my function, I decided that function will be purple, is increasing, the whole derivative is supposed to be placed above the x-axis, and it is. It is positive, the green part, now it's positive. Increasing positive. Yeah, we can say derivative is positive and function is increasing. I'm just using these colors now. Okay, now the purple function, which I decided that that's the f, yeah, you can analyze and take your time, is decreasing. From that 0 is decreasing, then the entire green function, which we decided that will be the derivative, is below the x-axis, negative, correct? And again, whereas the purple is increasing from this to this, and the green function, which is the derivative, is above, positive. And this one is below because the purple function is decreasing. Oh, too fast. Okay. Now, the only thing that we have to double check if the second derivative match. Now what I will look? I will look at my green function as a green, which is derivative, but I can call it my function, green function. Let's check where the green function has a horizontal tangent. Horizontal tangent here. Then the value of its derivative is supposed to be 0. And the red function has the 0 here, okay? Another green function, horizontal here, the value of the derivative is supposed to be 0. And yes, the red curve is intersecting x-axis, has the 0. And then we don't know what's going on here. And let's just check increasing, decreasing. The green function, my green function is decreasing from here to here, and the red curve is below the x-axis, is negative, and it's also negative here on that interval where my green function is decreasing, and green function is increasing here, and the red function is above. Okay, that we didn't use all of the tools, but just increasing, decreasing, and horizontal tangents and corresponding zeros for the derivative. It means, yes, that's the good order. Okay? You may definitely take time and try to analyze this, but the only thing that I use, again, increasing, decreasing situation and horizontal tangent for the value of the derivative being 0. Okay, thank you. Enjoy your higher derivatives.